This is question 42 of civil engineering paper of GATE 2014 forenoon session. A venturi meter having a diameter of 7.5 centimeter at the throat and 15 centimeter at the enlarged end is installed in a horizontal pipeline of 15 centimeter diameter. The pipe carries an incompressible fluid at a steady rate of 30 liters per second. The difference of pressure head measured in terms of the moving fluid in between the enlarged and the throat of the venturi meter is observed to be 2.45 meter. Taking the acceleration due to gravity as 9.81 meter per second square, the coefficient of discharge of the venturi meter is. So, in this question a venturi meter is given. The diameter at the throat is given as 7.5 centimeter and at the enlarged end is given as 15 centimeter, and it is installed in a horizontal pipeline of 15 centimeter diameter. This pipe carries an incompressible fluid at a steady rate of 30 liters per second, and the difference of pressure head is observed to be 2.45 meter. Now, considering all these data, we need to calculate the coefficient of discharge of the venturi meter. So, this question is from the topic of venturi meter. You may study about this coefficient of discharge of the venturi meter and working principle of the venturi meter and other related topics in lecture 12, applications of Bernoulli's equation, fluid mechanics by Professor Subhasis Datta, IIT Guwahati. So, venturi meter is an instrument to measure the rate of discharge of fluid flowing in any pipeline by creating the pressure head difference between 2 points. These 2 points are taken on the basis of the area of the cross sectional. The first point is taken here, the maximum cross sectional of this venturi meter, and the second point is taken as at the throat where the cross sectional area is minimum. So, as we know there are 3 parts in venturi meter: converging part, throat which is having the minimum cross sectional area, and then diverging part. So, the working principle of this venturi meter is Bernoulli's equation. While deriving this Bernoulli's equation, we take one of the assumptions is we assume the fluid is ideal in nature. The fluid is ideal in nature, that is viscosity is 0. For ideal fluid, viscosity is 0. But in practical, no fluid is ideal. All the fluid with which we deal are real in nature. All the in practical, we can say in practical all the fluids are real in nature, which is having some viscosity. So, due to this viscosity, when the fluid flows, there are some losses of energy. So, the actual discharge which we get is some lesser than the theoretical discharge which we derive by this formula. So, as we know the theoretical discharge which we got from this derivation, the theoretical discharge we get A1 A2 root over 2 GH by A1 square minus A2 square, where A1 and A2 are the cross section area at section 1 and 2, and H is the pressure head difference between these 2 points. But since this is theoretical discharge, the value of theoretical discharge, but in actual practice what happens, the actual discharge is lesser than theoretical discharge. That is why we introduce a we introduce a factor called coefficient of discharge into this QTS, that is theoretical discharge. Then we can calculate the actual discharge by multiplying this factor CD with theoretical discharge. This is theoretical discharge. So now in this question we have the value of this actual discharge, which is Q actual here 30 liters per second, 30 liter per second. So we can write this 30 into 10 to the power minus 3 meter cube per second. Now the theoretical discharge will be A1 A2 root over 2GH by root over A1 square minus A2 square. So here A1 is, so if we calculate A1, so A1 equal to pi by 4 into d square. So pi by 4, A1 is the at enlarged section, so pi by 4 into the diameter at enlarged end is 15 centimeter. So this is 0.15 square. So when we calculate it, we will get A1 as 0.0177, 0.0177. Similarly, A2 equal to pi by 4 into d square. So pi by 4 into A2 is the cross sectional area at throat, and the diameter at throat is given here in this question 7.5 centimeter, that is 0.075 square. So when we solve this, we will get A2 as 0.00442. So when we substitute all this value here in this formula, A1 is 0.0177 into A2, A2 is 0.00442 into root over 2GH, 2 into G is 9.81 into H, H is the head difference between these 2 points, which is given here 2.45 meter, 2.45 divided by root over A1 square. So A1 is 0.0177 square minus A2 square. So A2 is 0.00442 square. So this is theoretical discharge. So we got theoretical discharge here. When we solve this, we will get QTS, that is theoretical discharge, as 31.6 into 10 to the power minus 3 meter cube per second. So now we have the actual discharge value and the value of this theoretical discharge. So from this formula we can write the coefficient of discharge equal to Q actual by Q theoretical. So here CD will be, so CD will be Q actual by Q theoretical. So Q actual is here 30 into 10 to the power minus 3, and theoretical discharge just we have calculated here as 31.6 into 10 to the power minus 3. So this 10 to the power minus 3 will be cancelled out. So 30 by 31.6. So this will be 0.95. So the coefficient of discharge for this Venturi meter, we got the value as 0.95. So here 0.95. Coefficient of discharge of the Venturi meter is 0.95. So 0.95 is the correct answer for this question. Thank you.